few announcements. Actually, really just one announcement before we get started is about course review. I mentioned this in class on Friday, and I'll send out an announcement today. But as a reminder, the course review site is open. I do pay a lot of attention to these. I've used these to add computational tools to the class. There was a request for more examples, so I've added YouTube videos of worked examples. So please fill out your review. Let me know what's working for you, and things that I can change to keep improving the class. So as an incentive, when we get to 85% completion, I will give 2 hints to the final as an announcement on Canvas. So we're currently, I checked this morning, at 20%. So I know we can do definitely much better than that. So if you would, please fill out your course reviews. As reminders about assignments, right, because we're getting towards the very end here, we have the last homework and the CFD project are due Thursday now instead of Wednesday at 11:59 p.m., right, so just before midnight. And then the final exam will be a week from today in the classroom at 8 a.m., right? So a little bit earlier than our normal class time. That's our scheduled time for the final exam. Any questions on anything? Assignments, material, what we're doing before we get started today? All right. And I am flipping through the videos, but if you have a question, just feel free to speak up, unmute and speak up. Okay, so do we have just 2 classes left? We are going to cover things that are mostly about reviewing. Today's going to be a little bit different kind of review. We're going to review some of the key concepts we're going to use some of the key concepts that we've learned through the class to understand how airplanes fly, right? So we're going to look at that question of how airplanes fly through the lens of everything that we've learned in the class, and along the way, we're going to hit a few of the key concepts from throughout the chapters, and I'll call those out as we go through. And then on Wednesday, we're going to do our traditional lecture before an exam, where we go through and and talk about what topics could possibly be on the exam. But so today is aerodynamics, or how does an airplane fly? And this is covered in various places in your textbook, but really we're going to be using this primarily as a vehicle for some initial course review. So the central question here is, how does an airplane wing generate lift? And this is something that I think I told you at the beginning of class, that I feel like by the end of a fluid mechanics class, you should be able to give some explanation of how an airplane wing generates lift. So on the right-hand side here is a visualization, I believe it's from Van Dyke, Album of Fluid Motion, of an airplane wing with in a wind tunnel, with or an airfoil shape in a wind tunnel, with these streak lines visualized by some dye. And if you look at this question of how an airplane wing generates lift, most often you're going to hear one of a few different kinds of explanations: a Bernoulli explanation, a momentum explanation, or a rotation explanation. This has to do with the Magnus effect. And all of these are correct. So sometimes you will hear that there is maybe some kind of a controversy or something about like how an airplane wing generates lift. We'll talk about some fallacies and some things that are definitely wrong, but there's really no controversy between like Bernoulli and momentum explanations of lift. Both are correct. They're just different ways of looking at the same thing. There's different aspects in the Bernoulli or the momentum explanation of lift. You're just focusing on different aspects of the physics, but they are entirely consistent with one another. Okay, so there's really no controversy here. We know how an airplane flies. We can explain it using fluid mechanics. You can explain it and you can understand it using the things that we've learned this semester in class. Yeah, and there's really no controversy or tension between Bernoulli and momentum explanations. So we're going to use what we've learned this semester to look at all of these different ways to think about and explain what is lift and how does an airplane fly. So the most basic explanation that many of you have probably heard, if you have looked at this question of how does a plane generate lift, is probably something related to the Bernoulli explanation. Just by show of hands, how many people have heard this kind of an explanation before for lift? Yeah, I can see some hands in class, and yeah, okay, I see some hands on Zoom. Yeah, thanks. Yeah, so this is most common. Has anyone heard momentum as an explanation for lift? Just curious. Yeah, I see a bunch of no's. Okay. Momentum is probably okay. I'm flipping through the videos trying to see who said what. So momentum is actually probably my preferred, like, simplistic explanation of lift, but we'll get to that in a second. We're starting with Bernoulli because it's generally the most common. So as an example, the demonstration that you might have seen of this kind of thing is if we have a piece of paper, and if I were there in class, I would have brought something with me so I could do this demonstration for you, but it's pretty simple. We have a piece of paper and we blow air over the top of that piece of paper, right? We'll be increasing airspeed over the top of the piece of paper. And we know by Bernoulli equation, right? Remember from chapter 3, if we ignore any change in Z, right? If we ignore the potential energy, gravitational potential energy, if we increase the velocity of the airflow, then we have to decrease the pressure, right? So an increase in velocity causes a decrease in pressure. And this is, and then that decrease in pressure we could think of as causing a force, which, you might think of low pressure as maybe pulling this thing up, or really the high pressure on the underside is pushing this piece of paper up as you blow air across the top, right? So Bernoulli tells us something about how this piece of paper works. And if we look at an airplane wing, if we visualize flow around an airplane wing, then what we would see is this kind of a shape. So this is a sketch, really just a flow over an airplane wing. So we have some uniform flow coming in, the free stream velocity, we call it V infinity here. We've called it U, right, when we were doing our external flow chapter, the big, uppercase U. Far away from the airfoil, these lines should all be parallel and evenly spaced. I didn't, I guess in my sketch, I didn't make them all exactly evenly spaced, but these should be parallel and evenly spaced far away. And remember that if, so they're parallel and evenly spaced far away. And then as they reach the airfoil, we would see that these streamlines, they start crowding over the top and they spread out over the bottom, right? This is what we would see experimentally. And it's what we see kind of schematically here in this sketch. And if you remember from our discussion of streamlines, right, we can find these streamlines are, do not allow, or everywhere, sorry, parallel to the flow. And so there is no flow crossing these streamlines, meaning that the flow rate between any pair of streamlines in here is constant. And so we can, think of this thing almost as like a little channel defining where the flow is going. And as that channel here is narrowing, right, as those streamlines are narrowing, that means the velocity is increasing. Okay, so from this visualization and what we know about streamlines, what we've discussed about streamlines, where flow doesn't cross streamlines, flow is everywhere parallel to these streamlines. Because we have this nice steady flow here. The velocity here, right, because these streamlines are getting narrower together, they're getting crowded. That indicates that the velocity here is increasing, right, meaning the pressure is decreasing. And on the bottom side, the velocity is decreasing, which means the pressure is increasing, right? So this is telling us that velocity is higher over the top, just as it is in the paper example, and velocity is lower on the bottom. And right, so the crowding of streamlines means A goes down and B has to go up as long as it's incompressible. Ignoring gravity, right, because the shape of the airplane wing is an airplane wing is not so big that this delta Z is really significant. So when we ignore gravity, we see that the higher velocity over the top means lower pressure on the top and higher pressure on the bottom, right? And this lower pressure on top and higher pressure on the bottom gives a net force up on the airplane wing, okay? So that's kind of the Bernoulli explanation of lift. this works. I mean, this tells us something really important about how an airplane flies. The key lesson here is really useful. It says basically that the lift force that is produced by an airplane wing is due to the pressure on the surface. That's the lesson that we get from this Bernoulli explanation. So this is a plot or a sketch of what the pressure distribution looks like on an airplane wing. So this is pressure versus versus the x coordinate down the airplane wing. This is the pressure on the bottom surface of the wing, right, where the pressure is higher. And this curve here shows the pressure on the upper surface of the wing, where the velocity is higher, and therefore by Bernoulli, again, the pressure is lower. And the end result of this, lower pressure on top, higher pressure on the bottom, means that the airplane wing feels a net force up, right? Because remember, pressure, or chapter 2 concept, pressure is a force per unit area. And so if we take this, these pressure distributions, we integrate it over the area of the airplane wing, we end up with a net force that's going up, okay? So Bernoulli explanation of an airplane wing definitely works. But there are some problems with the Bernoulli explanation. And this is where we get into some of the fallacies that people fall into in trying to understand or trying to explain how an airplane wing works. And this is the fallacy that your TA fell into when Rob, when he was explaining how an airplane wing works during the class on external flow. Okay, so again, I want to correct that here. So the big problem here is it doesn't really tell us what causes the air to flow faster over the top. Okay, so I told you experimentally, if we look at streamlines over an airplane wing, we can see that there's crowding on top. We know because of what streamlines are that if there's crowding on top, then that means that there is an increase in velocity over the upper surface of the wing. But there's nothing in this explanation that tells us why the air flows faster over the top. The answer is sometimes given as this idea of equal time, and it's sometimes called the equal transit time fallacy. The idea is that there's a longer path here. If you see these streamlines, they're traveling a further distance. And then it's based on this idea that somehow this fallacy or this wrong idea that somehow streamlines have to meet, but this is entirely wrong, okay? The streamlines do not have to meet at the back of the airplane wing. There is no, it's not as if air starting here has to reach the back of the wing at the same time going across all of this. That is absolutely not true. In fact, for a well-designed airfoil, the velocity over the top is faster than what you would expect for this equal time fallacy idea. So this is a visualization from University of Cambridge. We're looking at these pulses of bubbles, and I'm going to try to pause this at just the right moment. There we go. And so they're all released at the same time, right, at the beginning. And so by equal transit time, if equal transit time were correct, we would expect them to all be in a line, right, at the end by the time they reach the end of the airfoil. But in fact, we can see that the bubbles or the tracers that were released over the top of the airfoil, they actually reach the back first. So they actually go, so the airflow over the top is even faster than you would expect by this equal transit time idea. So it's definitely wrong. Equal transit time is definitely wrong. So so this is like, first of all, this leads to fallacies about airfoil design, right? So the most famous one or classic example here is what's known as the cat's back profile, or Einstein's cat's back profile. So the story goes that Einstein, obviously, famous physicist, knows a lot about a lot of physics. And there was around the time that he was working, there's a lot of questions about like what is an efficient airfoil design. And there was a little competition to try to submit, the best possible airfoil design that would create the most lift. And his submission is something like this. It's called the cat's back profile. It almost looks like imagine like a cat, like a Halloween cat, with its back arched or something. And it comes from this idea, this fallacy of equal time, with the idea being, well, a longer path over the top is what gives rise to the the higher velocity, then I can make that path even longer if I really accentuate the curve in this airfoil. But when you actually, we know that equal transit time is wrong. At least this visualization shows that equal transit time is wrong. And this airfoil does terribly. So Einstein did many things very, very well, but airfoil, aerodynamics, airfoil design and aerodynamics were not one of the things that he did especially well. In the wind tunnel, when you actually test this thing, it does incredibly poorly. And part of that is because this equal transit time idea is wrong. Okay, so get that out of your head. But this is a little bit unsatisfying, right? Because like it doesn't tell us why air flows faster over the top. So we're still left with this, kind of hole in our knowledge or explanation of how airplanes fly, right? So we know that the air does flow faster over the top, and as long as that's true by Bernoulli, we can understand that there's a differential pressure which gives rise to a lift force. But we still have to explain why air flies faster over the top. So there's another explanation, which is momentum. And we can also use momentum and momentum balance in order to get another explanation for lift. And so the example here, this is kind of my sketch of like a hand in profile. But the example here is, imagine like putting your hand outside of a car window and like angling it a little bit. And you can actually feel, right? If you've ever done this before, I don't know, be careful, make sure there's no cars or signs or anything nearby. But you can actually, if you do this, has anyone ever tried this before? Just want to see show of hands. Yeah, I see a lot of, yeah, okay. So if you do this, this is the momentum explanation. So many of you said you hadn't heard the momentum explanation, but this is the momentum explanation, right? Because you can feel, or a demonstration of the momentum explanation. So you can feel the air being pushed down by your hand, right? And if the air is deflected down, then your hand feels a force up, right? Because the air is carrying momentum down, right? It's been deflected by your hand. It's just like the vane that we looked at, that's turning a fluid stream. That's exactly what's happening here. The hand here is deflecting the air down, and therefore, right. So there's a net momentum down, right, out of this control. If we draw a control volume around, there's a net momentum change where we're moving the air down, and therefore there must be a reaction force from that, right? F equals ma. There must be a force up. So this is kind of my favorite childhood explanation of lift. So as you all are going, maybe seeing some, or many of you are going to be seeing family members over the next couple of weeks, and talking to your family members about the classes you've done. Maybe you'll talk about fluid mechanics. I don't know. But if you do, maybe some of you are going to try to forget about it. But hopefully that's not the case. Then if someone's asking you, well, how does an airplane wing work? Momentum explanation, I think, is the clearest one to understand, because you can feel it. You can literally feel yourself pushing against the air with this way. And it's also, so you might have, I don't know if you look at the syllabus at all at this late stage in the semester, for the assigned reading for today is a book, Rocket Science for Babies, because it has this explanation, I think, in one of the simplest ways possible. And we're going to look at that now. So you don't have to have a copy of this book because I have the relevant pages here, Rocket Science for Babies. It's a great little series on like science topics. And I think this one really nails the momentum explanation for lift. So this is a ball. The ball is moving. Air can't go through it. Air goes around it, right? We've seen this before. Change the shape of the ball to change the airflow, right? This is what a streamline shape looks like. Change the angle of the ball to deflect the air down. If the air goes down, the shape goes up. This upward force is called lift. And this is the shape of an airplane wing. But how do we make the wing move forward? And this is where I say this requires combustion. It's beyond the scope of this class. So if you want to understand everything that's in this book, you need more than just fluid mechanics. But that first explanation, though, I'm just going to come back here. If the air goes down, the shape goes up. That's momentum balance, right? That's what we talked about for so long in chapter 3. That's what you dealt with on your exams. I see some things going off in the chat. Yeah, did I read this book to my kids? I definitely did. Yeah, my kids love it. I see Ethan shares the same sentiment. It's fantastic. They definitely love this book. They saw this coming out for a lecture today because I'm from home and they're sitting in the other room and they want to join and read it right now. You can definitely understand at least the first half of this and that deals with fluid mechanics based on what we've learned in this class, because this is exactly momentum balance. So let's look at this in the language that we've used in this class, right? So that's really simple language, which explains what momentum balance is. But so the main lesson here is that we can use a momentum explanation to understand where lift force comes from, right? An airplane wing, so by this momentum explanation, an airplane wing pushes air down, and so the airplane wing gets pushed up, right? This is the language that we've been using in this class, right? The math language that we've been using in this class. So lift is in the y direction. So we can start with a one-dimensional y momentum balance, like we have here, where we're going to say that the force in the y direction is the rate of change of the momentum contained within the control volume, right? So this unsteady component plus the sum of the momentum being advected out minus the sum of the momentum being advected in. So, right, force in y direction is the internal momentum change within the control volume plus the advected momentum into or out of the control volume. It's steady state, so we're going to say that the derivative with respect to t, the partial with respect to t, is equal to 0. These should be partials. And so we're also going to say that, let's say we take a control volume outside, like this is what our control volume looks like. And we're going to assume that we've drawn this control volume to be just big enough that there's nothing really traveling out of the top or bottom of it. So, so that the top and bottom, or that we've drawn the top and bottom along streamlines, let's say, so that, there's no momentum flux in or out of the top and bottom. We're going to assume that it's really, really wide, and we're ignoring what's going to happen on the two side faces. So we really just have to pay attention to this inlet face and this outlet face, right? Those are the two faces that we're gonna consider. And we're doing, again, the y momentum balance, right? So even though there's a large mass flux on that inlet face, right? So m dot is greater than 0. The velocity in the y direction, v, is equal to 0, right? Because this inlet face is upstream of the airfoil. It's undisturbed. There's no y component of velocity. So the sum of m dot v in is equal to 0. So now we have to look at the outlet face. And on the outlet face here, the flow has been deflected down, and we're just going to say it's been deflected down by some angle theta. Okay, so it's been deflected down by some angle theta. So we can then find the velocity. The y component of velocity is going to end up as v infinity times sine theta. And this is, if you remember, one of the hints that we gave when setting up a momentum balance problem is to try to draw your control surfaces perpendicular to the flow. Part of the reason is so you can avoid trigonometry in your m dot calculation. But in this case, if we were to do that trigonometry, because we have drawn the face, straight up and down in y, we haven't drawn it perpendicular to the flow at this angle theta. We end up with this expression for m dot, rho times v infinity cosine theta. So this is the velocity that's normal to that surface, times the area of that surface, which we're just for now going to call a swept. It's the area being kind of swept out in space by the airfoil, not the shape of the airfoil itself, but the shape of this control volume that we've drawn, which is kind of like, you can think of it as big as the region of air that's been disturbed by the airfoil. This, incidentally, is, if it seems confusing, it's because it's one of the things that's a little bit unsatisfying about this explanation. But just bear with me for a second. So if we put this together and we use this trigonometric identity, we end up with force of lift 1/2 rho a swept sine squared theta times v infinity squared. Now, if you remember from chapter 7, we write force lift as 1/2 rho times coefficient of lift times the planform area times v infinity squared. Does that make sense? Remember that? I know I wasn't here for that lecture, so yeah, okay. I see some nodding of heads. This looks very familiar, right? These look very similar, and what this tells us is that the coefficient of lift times the planform area that we've been using, right, in our description of lift, again from chapter 7, is going to be sine squared theta times the swept area, right, the area that's disturbed by the airfoil. But the problem here, right, just like with Bernoulli, the problem is, how do you explain the air going faster over the top or the bottom? The problem here is, how do we find that swept area and theta? Like we don't know that except by doing experiments, basically. And this explanation also completely ignores the details of the flow near the airfoil, right? Which is really what the Bernoulli explanation was primarily concerned with. So we can do a little bit better than this, and go a little bit further. And this is where we get to the rotation explanation for lift, which is another way of looking at it. So let's step back again now to some videos that we looked at earlier in the semester, when we were talking about momentum balances. We looked at, if you remember the Magnus effect videos, where we looked at like a basketball being spun with some backspin off of a dam and looking like it was kind of floating, or the KFC bucket airplane, if you remember that video explanation. But we said we can understand what's going on there, again, with momentum balance, just as we looked at just a few minutes ago. And we can understand that a rotating cylinder creates lift. So if we have flow coming in, right, some free stream flow coming in, and we have a cylinder like rotating at some angular velocity here, indicated as this capital gamma, we can see that on top, the flow speed is increased by rotation. On the bottom, the flow speed, right, increased by rotation because the incoming flow speed is augmented, right, or increased by the no slip condition at the top of the cylinder. You can imagine the cylinder kind of dragging the air around the top, again, by no slip condition, a good chapter 1 concept. And therefore we get an increase in flow speed over the top. And on the bottom, we have the opposite happening. The cylinder is moving in the opposite direction of the airflow. And we have, therefore, a decrease in velocity on the bottom, right? So there's our video. We can use Bernoulli to understand this because there's an increase in velocity on the top. Therefore, there's an increase in flow speed over the top. An increase in flow speed over the top means a decrease in pressure, right, by Bernoulli. Therefore, there's a net pressure force up. You can also use momentum to understand this, because this cylinder shape is throwing the air downwards, and that's how we talked about it in chapter, when we were discussing our chapter 3 stuff on momentum balance. Either explanation works, and they're both totally consistent. But importantly, we can now actually, we showed a bunch of equations with things that we didn't know. Here we know everything. And we can actually, we didn't go into this, but we can see that this generates a lift force that we can predict. The lift force is minus B. B is like the width into the screen here, times rho density times U infinity times gamma, the rotational velocity. So we can actually do math on this and predict exactly what the lift force would be. Right? There's nothing left unexplained here in this rotational thing. But the question is, what does this have to do with airplane wings? This is a cylinder. It's not an airplane wing, right? We saw a video, again, the KFC video, where they use cylinders as an airplane wing, but it doesn't really explain it. Question is, will this be on the final? I mean, we're using it to review concepts from class that will definitely be on the final. And you'll see examples from previous exams, some things that are a little bit related, but lift force as related to the coefficient of lift, that's definitely going to be on the final, right? Or definitely could be on the final. So yeah, and concepts from this definitely could be. So for one way to approach this is to first consider flow or how we could understand flow around an airfoil. So we could say that, well, the boundary layer is the only region where this is like the history of fluid mechanics, like where our understanding of flight comes from, is people first starting by asking, well, if the boundary layer, right, remember, is the only region where viscous forces are important, right? We said that the boundary layer in external flow was the region very close to a wall or surface or wing where viscous forces are important, where we're enforcing the no slip condition. But it's also incredibly thin, right? Remember, we said the boundary layer is about 5 centimeters or so thick on something the size of a 737, right? So boundary layers are incredibly thin, right? It's a chapter 7 kind of concept. And if this is something we didn't discuss, but the equations for Reynolds number approaching infinity, what's called inviscid flow theory, the Euler equations, we briefly mentioned Euler equations in class. Those equations are totally solvable. We can solve them actually with pen and paper. So, one question is, why not completely just ignore the boundary layer and use the inviscid flow equations, the Euler equations, to predict flow around the airfoil? And if you do this, this is what you predict. So this is just a sketch showing predicted streamlines for flow around an airfoil shape using inviscid flow theory. So if you take an airfoil shape, plug it into this inviscid flow theory, you can solve it by pen and paper. And this is the prediction that you get. Anyone, what's the problem here? Anyone just want to unmute for a second and just tell me what a problem is here? Yeah, Ethan, I see you've unmuted. I can't hear you though. Okay. All right. Well, thanks for your bravery. So problem is here, right? If we look at this trailing edge, there is air doesn't do that, right? It doesn't curve around this trailing edge, right? This is not what flow around an airfoil shape does. Right. So we have this curved streamline around that sharp trailing edge. In fact, if you have a really sharp point here, then your prediction would be that the pressure, the acceleration around that sharp trailing edge approaches infinity in order to get the flow to curve around this super sharp curve. And we know that can't be true, right? We don't have infinite acceleration anywhere in physics, definitely not in fluids. So what's missing here is rotation. So if in this inviscid flow theory, we add in some rotation, we say, instead of just simulating by pen and paper the flow around an airfoil shape, we simulate flow around an airfoil shape plus like a rotating cylinder that's sitting at the center of that airfoil shape. Then we start to correct this problem a little bit. And if we add a little bit more, then we can recover exactly what we expect to see based on our wind tunnel observations, where we see this nice smooth flow going off the back edge. And this works. This is what we actually see in real life. So if we look at startup flow around an airfoil, like an airfoil during takeoff, you can actually see this happening. So initially, if you were to look at flow around the airfoil shape when it's just started moving, you'd see something that looks a little bit like that inviscid flow explanation. And then as you get to like a really small time, right? If you're looking at it like at a very infinitesimally small time, you would see something that looks like this, where this is a little bit like that small rotation example. And now as we go to large time, we start to see something like this, where the flow again looks exactly like we would expect. And it's behaving, meaning that the airplane wing is all right, sorry about that. So it behaves as if there is a bound vortex or a vortex. Give me 1 second. All right. Somebody's I don't know, disturbed by the idea of a bound vortex. So we'll see that there is a we'll see that there is the formation, or the flow is consistent with there. We'll see that there is a the flow consistent with there being a vortex that is sitting right on the airplane wing. But the other thing that you would see from this is that that there was this flow curling around the back edge, and that flow curling around the back edge actually creates what we call a trailing vortex that gets shed off the airplane wing during that period when the airplane wing is starting to move. And so we end up seeing flow that looks like there's a bound vortex, or a vortex that's sitting here on the airplane wing, moving with the airplane, and a trailing vortex that's created during this startup flow. And we can think of that, this vorticity, is being created basically by the boundary layer. So the boundary layer is creating this, this set of vortices. And before computational fluid dynamics, this general idea of like airfoil plus vortex, airfoil shape plus vortex, is actually what was used to predict the lift of airfoils. And so it's actually what I used to teach in this class before we started teaching CFD, because it's a way of approximating the flow around an arbitrary shape. And it was what's historically used in fluid mechanics. But now, of course, we would use CFD, right? So we wouldn't do all this pen and paper math. But we can still learn something about this, that by combining flow around an airfoil shape plus this kind of a vortex, we can actually predict lift. And so this, we could actually predict the lift force of an airfoil shape pretty successfully here. And this startup vortex, so if we think about the flow around the airplane wing as being composed of flow around the airfoil shape plus this kind of vortex that's causing some rotation. That rotation is creating the lift. But the creation of that vortex creates a trailing vortex, which is actually which is created during startup. So here's a visualization. This comes from Prandtl. We've talked about the work of Prandtl in this class, but we can see this is an airfoil that's just started to move. And we can actually see this trailing vortex that's actually being created as the airplane wing is just starting to move. So we can see that. Sorry, guys. We can see that trailing vortex actually being created during startup, and that trailing vortex is actually left behind at the runway when the plane starts flying. Direct evidence that there is in fact a bound vortex, even though it's a little bit disturbing to maybe some of you, as well as some people here. It's actually part of a whole system of vortices. So if we think about an airplane wing, it has high pressure on the bottom, low pressure on the top. At the tips of the wings, the air will try to escape from that high pressure on the bottom towards that low pressure region on the top. And will actually swirl around the top, around the sides. And you can visualize that here. So this is showing the swirling flow, the vortical flow that happens as air flows from high pressure on the bottom to low pressure on the top, creating the swirling vortices. And this actually sets up this entire system called like a horseshoe vortex, where the tip vortices, which are swirling around, connect back to this trailing vortex, which is left on the runway, which connects to this bound vortex, which is sitting there basically virtually inside of the airplane wing. And this persists up to the point where this trailing vortex gets dissipated by friction and energy dissipation on the runway itself. So the time it takes for the startup vortex to dissipate by friction actually ends up placing a major limit on how closely airplane takeoffs can be spaced. So if you imagine you have a like a really big airplane, it needs more lift, therefore it has a stronger vortex, larger rotation, and therefore a larger time for the vortex to dissipate. And so big planes need larger spacing because they need more time for this trailing vortex to dissipate.